Hello, this is the Chapter 10 lesson. For this lesson you will need your calculator, and you will also need to print Table A6 from page 760 of the textbook. This can be done very easily by going to the ebook section of Course Compass, go to page 760, and then simply print that page. This is a chapter that we could spend the entire semester on. We're just going to condense it down into one simple lesson. Let's start off with a simple observation. It seems reasonable to believe that the heavier a car is, the lower its fuel economy in terms of highway miles per gallon. Well, to test that claim, we went out and collected data from 7 different vehicles. From each vehicle we recorded its weight and its highway miles per gallon. So you see there that the first car weighed 2,290 pounds and its miles per gallon was 37. The second car weighed 2,440 pounds and its highway miles per gallon was also 37, etc. If we just take a quick look at the data, we see that as we go down the table, the weight increases from about 2,200 pounds up to nearly 4,000 pounds. At the same time, the miles per gallon typically decreases from 37 down to 24. So it seems like the data does support our observation. As the weight increases, the miles per gallon tends to decrease. What we want to do in this chapter is to go one step further. Can we predict the miles per gallon of a car if we know its weight? That's the whole idea behind this section. Well, before we go any further, we need to define a couple of terms. The weight is what we call the predictor variable, and that's denoted by the letter X. Miles per gallon is the response variable, denoted by the letter Y. Now, variable means that its value could change from car to car. Every car is going to have a different weight and a different miles per gallon, so those are both variables. The weight is called the predictor variable because we are going to use it to predict miles per gallon. At the same time, miles per gallon is called the response variable because it is to some extent a response to the weight. Now, first thing we want to do is look at a graph of this data. So we're going to construct a type of a graph that we talked about back in Chapter 2 called a scatter plot. We talked about that type of graph in Chapter 2, but we didn't talk about how to actually construct it on the calculator. So let's look at how we can do that. So first thing we need to do is enter our data. So on your calculator, go to Stat, Edit, and choose option Edit, just like we've done before. Enter the weight data in list L1 and the miles per gallon data in L2. Now make sure you clear out those lists if there are any data in there to begin with. Start with an empty list and then enter your data. Okay. So once we've done that, we need to set up our plot. So select Stat Plot, which you do by hit the second button and then the Y equals, and then choose option A, which is called Plot 1. So we're going to turn on Plot 1, and we do that by highlighting the On option, hit Enter, and then next to Type, highlight that first option, hit Enter. Next to X list, we enter the list of data that contains our X values, which in this case is L1, and then Y list, enter the list that contains the Y values, which in this case is L2. Those should be the default values, but if they're not, you can change them. Now the last option there is Mark. That just chooses the type of dot that you want to put on the screen. We'll just choose the first one, which is the default. Okay. So once your screen looks like this figure there on the right, we need to hit the Zoom button, which is on the very top row of keys, and then scroll down to option 9, which is Zoom Stat. Now this will set our window to the proper dimensions so that we can see all the dots. Okay. Now when you graph it, it should look something like this on the right hand window. This looks just like the scatter plot that we constructed back in Chapter 2. Now this is not quite as nice as the one we saw in Chapter 2. The calculator doesn't label axes or put tick marks or anything else on it. But the weight is on the horizontal axis, miles per gallon is on the vertical axis. It's put a dot there for each pair of numbers. It went over the horizontal axis to the car's weight, and then it went up on the vertical axis to its miles per gallon, and it put a dot there. So what we see from the graph is as we move from left to right, the weight increases and the miles per gallon tends to decrease. That's the same relationship we saw just by looking at the numbers, but this graph is a lot easier to see. There's another observation we want to make, is that those dots kind of form a straight line that slopes down from left to right. That's a very important observation, and one that we're going to make use of in this chapter. So we see that there is a relationship, and we say that these two variables, weight and miles per gallon, have a negative linear correlation. Correlation is just a fancy name for relationship. Linear means they form a straight line. Negative means that that line slopes down from left to right. Now there are different types of relationships and different strengths of relationships. So if we look at these three graphs here, they all show graphs of variables x and y. Starting on the right, we see that those dots form nearly a perfect straight line. So in that case, those two variables x and y, we would say have a perfect negative linear correlation. If we look in the middle, those dots do form a straight line, but it's not quite as good a straight line as that one on the right. So we'd say they have a strong negative linear correlation. If we look at the graph on the left, we see they kind of form a straight line, but it's not near as compact a straight line as in the middle or the right-hand graph. So we say those two variables have a weak negative linear correlation. Well, if we have negative linear correlations, we also have positive correlations. So if we look at this one on the right, notice that those points form nearly a perfect straight line that slopes up from left to right. The fact that it slopes up means that as x increases, y also increases. So we would say that those variables have a perfect positive linear correlation. In the middle, we see another straight line, not quite as good a straight line as the one on the right. So they have a strong positive correlation. One on the left, we'd say have a weak positive correlation. Well, in these two graphs, we start with the one on the right. We say that those dots do form a pattern, but it's definitely not a straight line pattern. So we'd say that those two variables have a non-linear relationship or non-linear correlation. Non-linear meaning the opposite of linear. The one on the left, we see that those dots just don't form any pattern at all. It looks like they're randomly scattered about. So we say there is no correlation or no relationship between the variables x and y. Now here's some examples of some real data that come from our book. In the back of our book is a table of data from some different houses that were sold in one particular county. For each house they recorded things like its selling price, its square footage, its age, number of bedrooms, number of bathrooms, so on and so forth. So here's a scatter plot of the square footage of a house versus its age. And what we see as we move from left to right, the age tends to increase and the square footage tends to decrease. And those dots do kind of form a straight line if you use your imagination a little bit. So we'd say that the variables of age and square footage have a weak negative linear correlation. It means that as one of them increases, the other one tends to decrease. Here's another graph that comes from that same set of data. Here we've graphed its selling price versus its list price. Its list price is the price you'd put in the newspaper if you were trying to sell it. Its selling price is what it actually sells for. We see that those dots do form a very good straight line that slopes up from left to right, which means that as the list price increases, the selling price also increases. So I say that those two variables of list price and selling price have a strong positive linear correlation. Here's a third example from that same set of data. We have acres of land on which the house sits versus its age. As we move from left to right, the age increases, but we don't really see any pattern there. Acres doesn't tend to increase or decrease or do anything. Those dots just are more or less randomly scattered about. And so in this case, we'd say that those two variables have no correlation, meaning that as age increases, we really can't say anything about the acres. It doesn't tend to increase or decrease or do anything else. Okay, so we talked about different types of relationships: strong, weak, perfect, positive, negative. Next thing we want to do is measure the strength of the relationship. And we do this with the value we call R, which is called the linear correlation coefficient. It's also called the Pearson correlation coefficient. and it simply measures the strength of a linear relationship. It takes values between -1 and +1. If the value is negative, then we say there's a negative linear correlation. If it's positive, then there's a positive linear correlation. If it's close to 0, then we say there's no correlation at all. And the closer R is to +1 or -1, the stronger the linear relationship. So if we look back at these examples we saw earlier, starting with this one on the right where we had a perfect negative correlation, those two variables would have an R value of -1, or at least very close to -1. In the middle, where we have a strong negative correlation, we'd have an R value close to -1, but not as close as that one on the right. In the graph on the left, where we have a weak negative correlation, we'd have a negative value of R, but maybe not as close to -1 as in the middle one. If we have a perfect positive correlation, as in the right, the R value would be +1. Strong positive correlation, it would be close to +1. And if we have a weak positive correlation, it would be not as close to +1. In these examples where we have no correlation or a nonlinear relationship, we'd have an R value of 0 or very close to 0. Now the formula for calculating R value is very complicated, so we're not going to talk about it. Instead, we're just going to let the calculator do all the work. So after we've entered our data, which we've already done, we choose Stat, Tests, and then option F, called the LinReg t-test. LinReg t-test stands for Linear Regression t-test. Now the word phrase t-test is going to make a little more sense later on in the semester. We're not going to talk too much about what's going on there with the t-test. LinReg stands for Linear Regression, which we will talk about here in a bit. Now, depending on what type of calculator you have, it may be option F or it may be option E, but your calculator will have it. Okay? So you choose it like shown there in the figure on the left. The figure on the right shows the window how you should set it up. The X list is like before, the list that contains your X values, which in this case is L1. Y list is L2. Frequency, just leave that at the default value of 1. Now next, choose beta and rho not equal to 0. We won't get into what that means. The next option is REGEQ, which stands for regression equation. Just leave that blank for the moment. And then lastly, choose calculate and hit enter. And when you're all done, you'll get a window that resembles this on the right. You should see an arrow that points down, meaning you have some more options below that. Scroll all the way down, and the very last output there is the R value. We're going to talk about some of these other outputs, but for the time being, all we need is the R value. The R value there is -0.939. That's our R value for this set of data. Right above that is R squared, which is simply the square of that R value. But the one we're interested in is the R value, -0.94. Okay. So there's our R value. Notice that's close to -1, and so from that we would conclude that there is a strong negative linear correlation between weight and miles per gallon for cars in this sample. This is just a sample of 7 cars. What we want to now do is extend these results and ask the question, in the population of all cars, is there a linear relationship? Remember, the population is the large set of objects we're interested in. The sample is just a portion of that. So in this sample, there seems to be a linear relationship, but in the population, is there also a linear relationship? Well, we're going to use this table A6 to answer this question. Again, this comes from page 760 in the textbook. What we see here are 3 columns. N, alpha equals 0.05, and alpha equals 0.01. N is the sample size. In this case, it's 7. It's simply the number of pairs of data that we have, or number of cars from which we got data. So go down to row 7, or the one labeled N equals 7. That's the row we're going to use. Now, alpha, we're going to see this letter alpha quite a bit later on this semester. Alpha is a measure of how confident we want to be in our answer. It's what's called the significance level. And the smaller alpha is, the more confident we are. That seems a little bit contradictory, but that's the way it works out. Now the default value for alpha is 0.05, and so that's what we're going to use here. This number, alpha equals 0.05, is a number that we'll see a lot of later on in the semester. This is our first look at it. So we're going to use that middle column labeled alpha equals 0.05. So if we go to that column down to row n equals 7, we see the critical value of 0.754. So there's our critical value. Now what do we do with that? Well, if the absolute value of r is greater than the critical value, then we conclude that there is a linear correlation in the population. If the absolute value of r is less than the critical value, then we conclude that there is not a linear correlation in the population. So in this case, the absolute value of r is 0.944. Remember, to find absolute value of a number, we just drop any negative sign that's out front. So 0.944 is indeed greater than the critical value of 0.754, and so we would conclude that there is a linear correlation between weight and miles per gallon in the population of all cars. So in this sample there appeared to be a linear relationship. Based on that, we can conclude that in the population there is a linear correlation between weight and miles per gallon. So there's our conclusion. Again, there is a linear correlation between weight and miles per gallon in the population. Now let's talk about what this means and what this does not mean. First of all, this does not mean that weight causes miles per gallon. There are many factors involved. Things like the engine, the transmission, the tires, road conditions, weather conditions, all those things affect miles per gallon. Weight is just one of them. If you learn only one thing from this class, I want it to be this: that correlation does not imply causality. Just because there is a relationship between two variables does not mean that one causes the other. Too often in life we see that there's a relationship between two things and we immediately jump to the conclusion that one causes the other. That's not necessarily the case. In most situations there are many factors involved. We maybe have identified one of them, but not the only one. Okay. So let's talk about what this does mean. This does mean that we can use a straight line to predict a car's miles per gallon given its weight with reasonable accuracy. So if we know a car's weight, we're going to be able to use an equation for a straight line to predict the miles per gallon. That's what we call regression. The idea there is that we use the value of one variable to predict the value of another one. This is what we call linear regression. Linear because we're going to use a straight line. So the goal here is to find an equation for a straight line that quote-unquote fits the data. So here we see a graph from Minitab of the scatter plot of miles per gallon versus weight and a straight line fit to the data. Notice how that straight line doesn't go through all the data points, but it does capture the general trend of the data. That line is what we call the regression line. It's also called the best fit line. It's also called the least squares line. It's called the best fit line because it quote-unquote best fits the data out of all possible lines. It's called the least squares because of the criteria that we use for measuring how well it fits the data. Now an equation for a straight line, if you remember back to high school algebra, has a form that looks like this: y equals a plus bx. B is what we call the slope, a is what's called the y-intercept. Now in high school you may have read it as y equals mx plus b. Different letters, but they mean the same thing. Y equal a plus bx. Okay, now we want to find the equation for the best fit line. That equation is what's called the regression equation. And specifically what we want to do is find the slope b and the y-intercept a for that equation. Now the formulas for those values are very complicated. We're not going to get into it. We're just going to let the calculator do all the work. So after we've got the data entered, which we've already done, we go to that linreg t-test, which we've already done. It should already be on your calculator. If we scroll about halfway down in the results, we see A equals 54.69 and B equals negative 0.0079. Also notice there at the top of the screen we have y equal a plus bx. That's the form of the linear regression equation that the calculator is using. And it automatically calculates the value of a and the value of b. That's it. That's all we have to do. There's nothing more we have to do. Okay. So put those numbers in. Here's our regression equation. Y equals 54.7 minus 0.00976x. Now remember, back at the beginning of this lesson we defined that y was miles per gallon and x was weight. So the miles per gallon is 54.7 minus 0.00796 times the weight. There's our regression equation. Very easy to calculate. The calculator does all the work for us. Okay, now what can we do with that? Well, suppose a car weighs 3,000 pounds and we want to predict its highway miles per gallon. Well, what we can do is simply plug in 3,000 for weight, take it times the negative 0.00796, add it to 54.7, and we get 30.79. That number, 30.79 miles per gallon, is what we call the best predicted fuel economy for the car based on the data. So that is a prediction. It doesn't mean that the car will get exactly 30.79 miles per gallon. In fact, it probably won't, but this is a reasonable estimate. We also need to add this qualifier that it's an estimate based on the data, because if we had a different sample of cars, we'd probably get a slightly different regression equation and we get a different prediction. So that's how we use a linear regression equation. We simply plug in the value of one variable, do the arithmetic to get the predicted value of the other variable. Now, linear regression equations are easy to calculate, they're also easy to use, and they're often overused or used inappropriately. So let's give a couple of cautions. First caution is don't use the regression equation for weights outside of the range of the original data. In this data, our weights range from about 2,000 pounds up to 4,000 pounds. Over that range of weights, we know the trend of the data. They tend to decrease in a straight line, but we don't know what happens outside of that range. So for instance, if a car weighs 4,500 pounds, I could very easily plug that value into the regression equation, do the arithmetic, and get a predicted value of 18.84. However, that may or may not be a reasonable prediction because I don't know what happens to the trend of the data outside of that range. Okay. Let's illustrate our next couple of cautions with an example. Listed below are the heights and weights of 9 different supermodels. And we want to answer the question, is there a linear correlation between the height and the weight? So you see the x values are height, y values are weight. The x values are all around 70 inches. The weights are around 115 pounds roughly. So to first answer that question, we're going to construct a scatter plot and then calculate the value of r. So if we enter our data into lists L1 and L2 just like we've done before, now make sure that you clear out the data that was there originally before you start entering this data. Put the heights in L1 and the weights in L2. Okay. Then do your scatter plot. Now you won't have to set up anything because everything is already properly set up. All you need to do is hit zoom and then option 9 is for zoom stat. Don't forget to do the zoom stat. That's the most common mistake. People forget to do that. Hit zoom stat. And there's our scatter plot. Now notice that those dots do not form a straight line. So it doesn't look like there's much linear correlation between those variables of height and weight at all. Well, if we do our option F linreg t-test to calculate the r value, notice what we get is 0.36. That's positive, but it's not very close to 1. That indicates that there's not much relationship between height and weight as it appears in the data. Okay. So now just to analyze our data a little bit more using our table, there's our r value. If we go to table A6, there n is 9 because we have 9 pairs of data. If we use alpha equals 0.05, we get a critical value of 0.666. Well, our r value is less than the critical value, and so we would conclude that there is no linear correlation between height and weight in the population of supermodels. Have a small r value, that means that there is not a linear correlation between height and weight in supermodels. Okay. So what this means is that we cannot use a straight line to predict weight if we know the height. So if we know the supermodel's height, we're not going to be able to use a straight line or a regression equation in order to predict the weight. So this illustrates our second caution. If there is no linear correlation, don't use a regression equation to make predictions. If there is no linear correlation, then the quote-unquote best predicted value of y is simply the mean of the y values. So if I know a value of x, my best predicted corresponding value of y is simply the mean of the y values. I don't plug things into a regression equation. I don't use a straight line. I simply use the mean of the y values. So let's calculate the mean of the y values. We'll just do this purely on our calculator. So if we go to stat calc one variable statistics, hit enter, that will paste the one variable stats command back at the blank home screen, and then we enter that list L2. It's second 2 for L2, then hit enter. It's going to crunch the numbers, calculate the mean, standard deviation, other things for us. And here's our output, one variable stats. X bar, that's the mean of the numbers in that list. This list are y values, so this is the mean of the y values, equals 117. Looks a little funny to call it X bar when really they're y values, but X bar is just a generic term for the mean of the values in a set of data. So the mean weight there is 117 pounds. So that would be the best predicted value of y. Okay? So what does that mean? Well, suppose a supermodel is 68.5 inches tall. Find the best predicted weight. Well, the best predicted weight is simply the mean of those weights, which is 117. So if the supermodel is 68.5 inches tall, our best predicted value of the weight is 117. Likewise, suppose a supermodel is 70.75 inches tall. Find the best predicted weight. Well, it's going to be the same answer, 117 pounds. I'm not using a regression equation or a straight line to predict weights. I'm simply using the mean of those weights, 117. Okay. Our third caution here is that these results apply to only the population of supermodels. They cannot be applied to the general population of all women. Our data comes from only supermodels, so we should only apply our conclusions to the population of supermodels. In the general population of all women, there may be a linear correlation. I don't know. Our data doesn't have anything to do with just general women. In general, don't apply conclusions to population larger than the population from which the sample came. This is a very general statement, something that we'll see more of later on in the semester. So that's it for the Chapter 10 lesson. The homework at Course Compass is simply Chapter 10.